Let's see.
Had nightmares for a week. Troy used to do that once. I don't know if it was exams, but he made you type out hex values on the iClicker when you were dealing with like the machine code.
Nice.
Yeah,
Okay.
I did that for like
days.
I got like hex addresses and stuff like that. Just your clicks.
You had to be quick too, because they did give you a lot of time.
Wow. Okay, so I want to talk about the sort of the lifetime of a process today, starting from before the process is born until it dies, and we'll maybe revisit its burial as well, the collection of the zombie resources. But I thought we'd take it in, put it sort of in the context of what specific execution. So I'm going to run. Let's see. Do this, and I'll just type echo hello, right? And when I hit enter here, the question is what's going on. But maybe before even we get there, what's going on right now? Let's see. So what processes are currently running? SH is running, okay? It's running in the sense that it's at least runnable. We don't know exactly right now what's running, perhaps. Is there any other process?
When you were typing, there would be interrupts firing for.
That's not a process, though. Right. If I hit Control P, oh, there. It actually lists the running processes. So we have init. Init is always the first process, and it's always around. Right? That's the one that started SH, and I think if SH dies, init will start another one, if I remember correctly.
I think if you can control D, it will keep starting SH.
Okay, yeah, that seems... No, actually, that seems very unlikely. Control D doesn't do anything right now on this machine. We don't have signals. Oh, unless SH is listening for Control D and calls exit.
Yeah,
If you do.
it's always saying starting SH when you
Let's see. Okay, so Control D. So SH must be listening for Control D then. Actually,
init is starting SH. So
yeah, it's not a signal actually. I take that back. Control D is the end of the file and it's not handled as a signal. So it's actually closing closing the standard in for this process, I think is what happened. But anyway, that's not what we were going to do. We were typing echo hello, and so we have sh and init running, runnable. So init isn't really running, it's waiting. We haven't really talked about waiting yet. We'll see that later. It's in the state waiting as well. It's not runnable right now. You can't start it. What about sh? Is that runnable? We have some yeses. No no's. The answer is no. sh is also waiting. It's waiting for keyboard inputs. Right? It's currently called syswrite, but syswrite is a blocking system call. And so it can't come back. Sorry, it says read, naturally, not write. It calls read because it wants to get the next input. Right? And so if we take a look at sysread, you'll see it's we're waiting for the end of the line, I think, and until we get an end of the line, we're not going to return from that system call. Yeah.
So if it's not SH doing it, what's making the cursor blink?
This is the display adapter.
Okay.
It's not even in the code of the kernel. Well, I mean, in the emulator, of course. This is a graphics display, so I think the OS X is actually blinking that at some point. But that's just because it's an emulator. All right, so the CGA graphics text mode has a cursor that blinks. Right, okay. So there's actually no runnable process here. So what are we doing? Computer's doing something.
Just waiting.
But how does it wait?
It's still just looping and going to the B table to find a runnable process.
It's in the scheduler, running desperately round and round. And if you ever, say, had a late night on a couch trying to finish up a homework, and it got really hot, right, on your lap, which mine does, then that's because we're running around the scheduler.
I think it's print out a warning saying I'll loop run for 1,000 cycles or something.
Does it print a warning? I don't see any warning.
No, not in this, but in the terminal it starts the emulator.
Huh. Oh, mine doesn't do that either, but okay. Maybe that depends on what OS you're running that on. Either way, yeah. So a more sophisticated OS might halt the CPU, perhaps. There's an instruction halt, and then it just doesn't do any more instructions. Or it might wait for, there's a monitor mwait kind of instruction where you say, okay, I will do nothing until someone writes to this memory address, which presumably an interrupt could do or something like that. So anyway, we are just spinning around.
100% CPU usage.
Oh, you just checked it. Okay, good. Yeah. See what it says on mine.
That works 100%.
Right. So there's the one.
Yep.
But it's not using 100% of my machine because I have more cores than that. Oh, it doesn't actually show it. But anyway, so this is for one, yeah, 101%. That's funny. So here's the total CPU usage on the machine. So they kind of divide that by the number of cores. Number of threads, not cores. There's hyper-threading. There's 2 threads per core. So how many is that then? 8. 8 threads. Okay. Oh, by the way, hyperthreads look exactly like cores to an operating system. There's essentially no difference. There's only a performance difference. All right. So let's hit enter. I don't know what the 7s are all about, but I get that a lot. So what happened? Well, SH was waiting for the sysread to return. It returned, and then what? We got a fork and then an exec, right? So we need to take a look at those. Fork creates a copy of SH. What does it mean to make a copy of a process? Right? We have some amount of process state. It needs to have a completely independent copy of all of that state. Almost an identical copy, but not quite. I can think of one thing that's different. 2 things that are different.
Process ID and parent ID.
Process ID and parent ID, right. And then, of course, the address, the physical pages used and that sort of thing, but that is kind of under the covers. All right, so let's start with fork. I'll just kill this to save some battery power. Yeah, I have to be a little careful because I was just working on a homework solution. All right, so let's see. It's in proc.c, I think. So I'm going to skip a few steps, right? You know what's happening with a system call by now, so we're not worrying about that. But what's the state that we need to copy? We need to copy a page table, right? We need to copy, any other ideas? File descriptors, yeah. In fact, we're not really copying them, they're actually shared. So we're kind of putting pointers into the same open files. Anything else? All of the memory, right. So there's actually a couple different ways to do that. In Linux, I think, and they do a lazy memory copy. So when you fork, you read only all of the pages of the parent process, except maybe the stack. But I think you read only everything. And then you have the child just point to all the same pages. Just like we're going to do in our next homework, right? Where we are pointing many pages to a single physical memory frame. In the lazy fork in Linux, they have both processes pointing at the same physical memory, and as soon as one of them tries to write to one of those pages, then they do the copy and write. It's really nice if you have a very large process and you want to run a few copies of it. In our case, we just have to copy everything. So not only do we copy the page table, we also copy all of the physical memory frames that were mapped in. Anything else? Registers, right, and that actually means the trap frame in this case, because the process isn't, well, it's running in some sense, but it's not in user land at least. So the register contents aren't going to change. They're sitting in the trap frame waiting to be restored. So we have to copy the trap frame. So let's take a look at fork then. All right, so we may as well dive into allocproc. So that just finds an entry in the proc table, but there's a little bit more work to do once you're there. So we look for an empty entry, right? An unused state process, and then main thing being we need to allocate kernel stack. Any process needs to have its own stack for the kernel. That's where the trap frame goes, and all of the stack frames for handling a system call or an interrupt while this process is in use. All right, so we set up the stack pointer already. That's actually happening a little bit later. Let's see. So we have just a local stack pointer here. This is just a local variable. Later on, that gets assigned. Okay, so we set up where is the trap frame. Normally, when you come back from a process, we set this trap frame value, right? When you have a system call or an interrupt, we get into the kernel, we set that trap frame. I think it's in fork. Sorry, in trap, right? We get the stack pointer coming in, and we assign it in trap. But it needs to have some sensible value in the beginning too of the life of the process. All right, and then we need to know where to go to. So if you're just starting to run, we need to know, like, how do we get back from our system call? Because we aren't the same. We're the same process in user space, right? We should look exactly the same in the user space, but we can't very well act the same in the kernel. Right? In the kernel, one of us is the parent, the other one is the child. There will be different things that we have to do. So, so here we're saying, how do we get back? Right when we start running the child, what are we going to do next? Well, we have to get back out of the system call. This is the second return out of the fork, right? When you fork a process, you return twice. You enter once and you return twice. This is how we make the second return happen. All right. Set up the context, nothing much there, and then let's see now. Yes, of course. So when we're switching for the first time to this process, we also need to know where we're going from switch. Normally we would go back into where we called from, but we didn't call from anywhere. Right? When you're switching away from a process, you switch into the scheduler from somewhere. But in this case, we didn't switch from anywhere. So there's a special place where we go back to the first time. This is fork routes. Okay, they use this for for a little bit of initialization too. I forget. We'll take a look at that maybe. Let's back up. Okay, so we have a process that is almost alive, but it's not really a copy yet. All right. So far, we just have a process that you could, in principle, try to run, but it doesn't have any instructions, so it'd be a little weird. We have an EIP set to. Actually, what was it set? Let's take a look at that. I think I saw EIP being set. That's the context EIP. We don't have a trap frame yet. No, so we can't run this yet because we don't actually know where we would start this in user space. Like, what's the next instruction? So we're not quite there. All right, let's back up. So we have a sort of a process. Now we need to kind of populate it. So here, copy all of the user virtual memory. And then, okay, maybe we should look at that. Well, let's do a breadth first sort of thing. So we copy all of the user virtual memory. This is the page table and also all of the physical memory frames. We're copying everything, allocating new frames for every mapped in page. Okay, size, we're just sort of duplicating some state here, setting up the parent. This one's interesting. I love this syntax in C. Anyone remember what it does? Yeah, so this one dereferences the trap frame, right? And what's going here? Here we're dereferencing another one.
But it's setting the address to what the other one just dereferenced.
There's no address left here. We've dereferenced both addresses. Exactly. We're copying over the values, but what's really cool about this is the value is a whole struct. It's like 64 bytes, or no, it's more. It's a long one, right? All of those register values. So we're copying the entire struct with this one assignment. Something you would usually expect in Java or something, perhaps. In fact, in Java, they're not really good at copy by value at all. It's all by reference, right? So I guess in C++, maybe you might expect it, but it's very rare to see this sort of thing in C, or at least it doesn't feel quite natural. So this thing expands to a whole lot of moves, right? Move the first word to EAX, and then from EAX to the destination, and then next one. Or potentially to the rep move S. There's a rep means we do this many times. This move S is string sort of thing. You can tell it, oh, I want to copy 100 bytes. You put 100 in ECX, and then it'll just do it for you. Either way, it does result in a whole lot of action. Depends on what GCC decides, what it actually does, how it actually does it. We're supposed to return a 0 from fork if you're the child, right? So set that up. File dupe. Let's see now. Yes. I misspoke again about the file descriptors. All right. We do copy the file descriptors, but the files are the same. So they have the same console, so to speak, but they do have different cursors into the console.
But they start at the same spot where I pulled.
Yeah, they start at the same place, but yeah, they would have to have different. I don't actually know what happens if you have two of them writing. Let's take a look at file dupe to get this right. Before we get to file dupe, let's just finish this thing. All right, so we're just setting up a little bit of more state. We wanted to do this copy UVM, so we don't forget about that. All right, so this is the kernel mapping, we're setting up again, and then for every page in the process, you'll notice there's no mmap here, no mmap, right? And in our MAP homework, we didn't really support fork. So if you were to fork an M-mapped process, we would lose the M-map region through here, right? Because we're only copying the pages that are between 0 and size. So we find the entry, and then allocate a new page, and then copy in with the same flags that we had the entry for, copy it in at the right, or map it in at the right place. Here we copy the contents and then map it in at the right address. So page by page, all of the text and the heap and the stack get copied.
Small question. I mean,
Yeah.
a little tangential, but copy here and in other places also, right? I think it's in work itself. We could go to generally.
Can you speak up a little bit?
I'm sorry. I mean, I've seen go-tos being used in a couple of places, and generally it's considered to be bad practice.
No. Go-to is totally fine. You know, there's this title, very famous paper, I think it was by Dijkstra, Go-to Considered Harmful. It was, there was some limitation to how long the title could be. I think what he meant was go-tos that go backward are considered harmful, but that's too long, right? The problem with go-tos that go backward is they make a loop, but it doesn't look like a loop in the code, and now it gets very confusing, and you can make all sorts of spaghetti. If you only go to down, then generally you'll be fine. And this is a very common practice to go to error handling code or cleanup code toward the end, and I wouldn't worry about that at all. What's that? Yeah, there would have to be a lot in the Linux kernel. I don't know that I've seen more of it there than elsewhere, but yeah, I guess you would expect in systems code that there's a lot more error handling than there would be in a pure algorithm that's factoring integers or something. Yeah. So perhaps there's more of that because of that. Okay, backing up. Yeah, we were going to take a look at this file loop, see what that actually does. I think I've done this in the past, and I forgot what it's doing. Okay, very good. Very good. So it is a shared one. I thought so. It's not actually duplicating it, it's just... good. All right. So it is a shared. The only way it could work really for the console is it has to be a shared one, because imagine you're writing a character to the console, and then another process is writing a character. Like, they both have access to the console at the moment. They would overwrite, and that would get really weird. So the offset would have to be a shared variable, and that's what it is here. So now we have a reference count that's going up, but we just have pointers in the process pointing to an entry in the F table. The F table is just like the P table. It's a statically allocated array with a bunch of unused entries, and you scan until you find one that's unused if you need a new file. A new struct file, that is. Okay, that's a relief. And I think I've forgotten that once before. Okay, so now we have our file descriptors. This means both SH and our current program are now waiting for, or are using the same standard in and the same standard out, standard error. So that seems a little strange, right? So now what happens if I'm using cat, let's say. Let's just see what cat, the expected behavior of cat is like this. I say ls, and it types ls, right? Because cat is listening on standard in. If I don't specify a file, then it opens that and listens to that instead. And then it writes it out to standard out. That's what cat does. Let's see what. So now one cat is listening for the other cat and writing it out. So this should be the same behavior, right? It's just that it went through the pipe between the cats. All right. So why is it that SH isn't trying to run the program hello. Because it's got the same standard in. SH is still running. We forked. Sorry?
The state is not runnable, only one process will be running, right?
No. Well, okay, so the state is in fact not runnable. But it's not because only one process, like the OS does not decide that only one process gets to run. But there's some other reason why SH is not runnable at the moment.
Just wait until the child dies before it does anything.
Exactly. So the SH actually does fork, exec, wait. Right? And so that's the only reason it's not acting on the standard in inputs. Okay, so we got to fork. We got through fork, I should say. And so now we've added a new process to the P table in state runnable. It has all the same trap frame, same memory, same file descriptors. So if we start running it, if the scheduler at some point switches to this process, we ought to get to this fork ret. And I think on top of that, there was then a trap ret. We can have a little, actually, let's just get in there one more time. We kind of have a little fake stack here. We have, this is what we're going to start running. After the switch, we start running this. But then we have the stack that says at the very top, go to syscall trap ret. So from fork ret, when it returns, it'll go to syscall trap ret. So it's like 2 levels of returns there that we've faked. Okay, but what happens after this? So, so we finish our fork, and now which process are we going to run? We have 2, and we have 3. We have SH, but it's waiting for us, so that's okay. And then we have our newly, oh, actually, SH is not waiting for us, I'm sorry. This is SH. We're forking. We're still in SH forking. We didn't get to exec yet. So now we have 2 copies of SH, the parent and the child. Which one are we going to be running?
First.
The parent, exactly, because we didn't call switch. The only way to get to run the other one is to call switch one way or another. And so actually, if we look at trap, we get in here, right? This is our sys fork will be in here, and then we do the syscall, and then we return. We didn't even look at whatever's happening below in trap. Okay, so we're getting back into SH, and then into the parent SH, and the parent SH then calls wait, and that's that, because it'll wait until the child exits. So we don't have to worry about the parent parent SH. All right, so now we have the child SH. It's still just SH, right? We just copied SH. But there's a little if condition in there that says, oh, if the return value from fork is 0, that means I'm the child. That means I should change my identity to become the new other process, which in this case was echo. Right? So how do we change to echo while we run sysexec? Right? If we want to become this new process. Exec is it's a strange system call to be calling, because you essentially kill yourself and become something else. Right? And after that, there's nothing left of your register values or your memory contents or anything except the file descriptors, which actually remain. So when you call sysexec, you don't return. Right? With fork, you return twice. You call sysexec, you don't return. Same as exit. Okay, so let's take a look at sysexec. Just to be safe, I think we'll go to sysproc first. Oh, is it not in there? Okay. So where Where is sys? Oh, it's in sysfile. Sometimes I have a hard time deciding where it ought to be. There it is. Okay. All right. Interesting. Right. Okay. So exec is a little trickier than other system calls because it passes in an array of strings. That's the argument, right, to exec. The format of this array is such that you have a bunch of strings and then you have a null pointer. A bunch of pointers and then a null pointer. Then you know that the array has finished. You don't say how many elements there were in the array. So here we're going through this argv array that was passed in, and we have any number of elements, and we stop when we reach the 0th one. So what we're doing is basically we're copying all the strings from the user, or are we actually copying just a string pointer? Yeah. From the user stack, we're getting all these string pointers, and we're sticking them inside of this local array here instead. This is just so that we can sensibly, just like with every other system call, just so we can make a sensible function call, right, with normal values that are on our stack. Okay, so it's not different from all of the other sys underscore functions. It's just that it's a little hairier getting all of those strings out. A normal sysexec would also have this environment variables. You know, everything that's from inside of bash, for example. Actually, I'll just show this. So if I say set here, oh, this is really messy. All of this stuff are the environment variables. They're passed in with exec as well. But we don't have exec in, we don't have environment variables supported in x86. All right, so we'll go to the actual exec then. So here we already have an existing process. What we need to do is get rid of all of its memory contents and then find an executable that was specified and pass in, somehow read in the contents of that executable, stick it in memory, and then start running at the right place. Okay, so we start out with okay, here we're just checking that this file actually exists. Otherwise, we can't exec, and then we return a -1. Okay, so if it does exist, we want to make sure that this is a readable what's it called? Executable and linkable format, right? ELF. So reading a little bit and making sure that it starts out with this ELF string. It's not a string; it's a 4-byte or 8-byte integer. All right, and then as before. Oh yeah. Hold on. Oh, okay, good. I was worried that we're assigning pagedir to 0, but this is not our proc pagedir. This is a local variable. We're setting up a new page directory without having it assigned to the process just yet. So we're setting up a new page table, starting with the kernel mapping as always, and then the ELF format has a bunch of sections. I think we've seen this in the past, but let's take another look. Take a simple ELF executable. Actually, why don't we take echo? Oh, underscore echo. Oh, and by the way, in Linux or in bash, I believe echo is not a binary. Echo is a built-in command inside of bash. but it's just a normal program in x86. All right, so come on. What is this? Scroll. Okay, how am I supposed to scroll this? All right, so let's see what we have in here. Oh, did it not even run it? Okay, that's we'll go like this instead then. All right, here it is. So the ELF, it starts out with, I think this, I wonder how that reads out, ELF. That's ULF, but is that an EA? Yeah, that looks kind of, 5 looks kind of like an E, and the 4 is an A, and then we have, oh wait. What kind of byte order is that? I don't know how you get to ELF.
I guess it's the 573.
5, 7, what?
ELF. Yeah, so 5.
So is that ELF? Yeah, and so it's 4 ELF.
Yeah.
So in that case, this is in big endian, right? We start with anyway. There's the magic. Well, maybe this is also part of it. Should look that up. All right. So the header, it doesn't look like this, of course. This is all binary. It's only a few bytes, like maybe 64 bytes or something. Size of this header, 64 bytes. Yeah. So we just printed it out nicely here. But it says, okay, there's program headers or section headers are coming a little bit later. And also, by the way, when you want to run this, you should start at, where's the entry? Entry point address. You should start running at address 0. Right, so we'll set EIP. We'll see this in code at some point. We set EIP to 0 because that's where the first instruction is for this program. But every program could potentially be different. Okay, so what does it say in these section headers? I think the most important one that we'll worry about is the text here. All right, so we're saying the text should begin at address 0. In this file, it starts this far in. All right, so we should copy bytes starting from this offset in the file to the virtual memory address 0 and up, and we should copy this many bytes. So now we have all the code in our memory, if we've done that. And then there's also a read-only data. That's stuff like strings. If you have a hard-coded string somewhere in your program, that's a good place, a good thing to have in your read-only data section. Your data section is global variables, read-write global variables. And then there's a BSS section. Does anyone know? That was a little different. Yeah, uninitialized data. So it's a global variable that you didn't say what value you should have. And by default, then it becomes initialized to 0. It's handy if you make, say, an array that's a megabyte. Because if it was sitting in the data section here, even an uninitialized, you could imagine putting it in a data section, but then the file would be 1 megabyte large. Even if it's a very simple program, you statically allocate 1 megabyte, it has to go in somewhere in the file, so you have a 1 megabyte file. But if you don't initialize it, you can just stick it in your BSS, and we just know, like, oh, starting at this address, right, there should be this many bytes of zeros. That's it. Right. So that's a lot more compact. Actually, I think this could be fun to illustrate. Let's try it. that should do. Nah. Oh yeah, okay, that's fine. Yeah, so it's not a very big one because I didn't initialize it, right? So that's 8 kilobytes. But what if we try to initialize it a little bit? It's enough to initialize just a little bit, actually, because we don't. It can go in the BSS or not in the BSS, right? It'll be in data or BSS. So I'll just initialize the first one to a 1. And in fact, I think that this, I don't know, if you put a 0 here, I think that means you want it all to be zeros. I've seen that somewhere. I don't know why. But maybe it's just that it's going to go in the BSS. Could be that. And because it's in the BSS, that's probably what it is. I don't know. Anyway, with a 1 in here, it must mean I want at least 1 1. And the rest, I think it probably is going to be zeros. But I could be wrong. We can look at that too. Anyway, let's compile this. Ooh. There it is. All right. And so it has to be like that because when you're loading this program, right, the elf header, there's 2 ways you can describe what should be in your statically initialized or statically allocated data. It can be uninitialized, which means it's zeros. Or it could be initialized, which means we have to have the entire initialization array in there. Let's see if it was all full of 1s or full of zeros. Is that it? No. This, no, there's got to be one of those big gaps somewhere. 1 million. Here. So this has to be the uninitialized. You see that this is the offset. So from 4 kilobytes up to very large, it's all zeros. The star just means the same thing repeats over and over. That's a thank you, what was X? Okay. So that's the first byte, the 1 that we initialized. So I think if you set I want a 0 in there, because I read this, like people do this, and the compiler doesn't get upset if you say with a 0. Let's try that too, just to because now I'm too curious. I think if you put a 0, it'll still be the small version. It'll be the 8 kilobyte because the compiler is being clever. But let's see.
What if you put 2 zeros?
0, comma 0. Ooh. We'll leave that as homework. Anyway, so it has the same effect as not initializing it, right? Except at compile time, at runtime. No, at compile time. When you want to dereference some elements in this array, if you put it to a 0, now we also implicitly made all the other ones zeros and everything's fine. Okay. Anyway, where were we? Yes, we were in exec. So there are all these section headers, and we want to find the relevant ones, right? So we're loading in the text and the data, and actually we're probably loading in everything. Let's see what it's got here. So we're trying to read whatever, let's see, from the header. I guess we're reading one program header at a time at a certain offset. All right. We read the header. If the type isn't interesting, skip it. If it doesn't fit, we have some errors. Okay, here. Allocate some space for whatever it said. So this is what we're just looking at, this many bytes, right? So we allocate that many bytes with alloc UVM. All right, so this one, you looked at it, it only does, it grows the size from this to that, is it? Yeah, that's gonna be it. So it's just kind of growing it if necessary. And then we're copying in something, right? We're copying into the address that was specified from the file. This is the IP, is an inode pointer. We'll get that more specifically much later. And what is it we're reading, what bytes are we reading from the file, right, and how many. So we're just following the specification of the file. There isn't much going on in here. We're just saying, okay, that section header there. We'll go take another look at this. Right. So we're actually loading in this comment thing and the debug A ranges and whatnot, and we're not really using those. But the executable says, this is how you load me, right? And then how do you start me? Well, you jump to the entry point. Let's find that too. So this is still in exec, I think. Ah, okay, very good. I've talked about this at least to some people in office hours. So, so now we have the text, right? But it didn't say anything about the stack in that executable. The stack isn't really part of the executable. So now we need to allocate some room for the stack. We first find the next page up, because we're going to play with entire page frames here. We allocate 2 pages. They do here, but then for one of them, they say this one is not user accessible. So this is clear PTE U bit saying the user may not access this. We've actually allocated 2. I don't know why. They might as well have left one empty. It could be not present as well, but all right. So we got a text, and then we got one supervisor only page, and then comes the stack. So the reason to do that is that if we do anything bad on the stack, right, we get a stack overflow, then you go over that 4 kilobytes. Well, now we have a choice. We can either do unspecified behavior by overriding our code, right, and anything could happen, or we can just kill the program. And this is a way to detect that it went over, right? The moment you try to write to the next byte below the stack, that's a supervisor only frame. So now we'll get a page fault, and when we see this happening, well, then we kill the process. Okay, and then finally, exec has, oh, maybe not finally. Exec in the end calls the entry point, right? But the expectation is you have parameters on the stack. The command line arguments go on the stack. So here we're copying in the command line arguments, and they need to go to the new user's stack, right? So that's the copy out for each string. We have to copy the string, actually. It used to be sitting in the SH, the old SH, which is calling this. The strings are in that process's address space. So now we're taking the pointers. These are just pointers, which are in the kernels, on the kernel stack. We're copying the actual strings from the previous process into the new process. Did we already switch? No, we didn't. So copy it out. We actually have to specify which page directory, so we can do it kind of manually, that copy. I think that one's doing the what's it called? Walk page dir. It probably has to do this manual walk page dir in order to copy the strings to the new process. But let's take a look. Yeah, UVA, user virtual address to kernel address, given a page directory. I bet you this one calls walk page dir. There it is. All right. So in order, so what am I talking about here? We're still running the SH. Nothing happened to SH yet. We're just setting up a new page table full of stuff. And we need to get some strings in there the way it should be. But we haven't set the CR3, so we don't have access to that memory yet. We don't have that memory layout of the new process that we're setting up. So to manually get that contents into the process, well, we use copy out. Okay. So this now. Here we're just putting a pointer on the stack. This is the user stack, right? We're putting a pointer to the string that we just, it's not the stack pointer thing. Oh, it is a stack pointer and the string pointer. Yeah, we're putting the strings on the stack because where else are we going to put it? We've got to put them somewhere. We're putting them on the stack. And then we're yeah, okay. So a little bit more trickery happening here. Where is it? I think it all has to get copied at some point. Yeah. Right. So this is also a kind of a temporary stack that we're setting up. It's going to be the end of the stack. And we're copying that over at the end. All right, we can maybe skip a couple of those things. First argument to main, second argument to main, right? argc and argv getting populated here. And finally here we're copying out the remainder of the stack, the return address, and I don't know why argc goes on the stack too. It ought to be one of the two. This seems like a bug. This is probably left over from the 32-bit implementation. Arguments to the function go in RDI and RSI. They don't go on the stack. So I think this we can wipe out. It's not necessary. Okay. So anyway, now it's time. We set everything up. We have the new memory layout. Everything's good. So now it's time to switch our process over to do the different thing. Assign a new page directory. We've already saved a pointer to the old page directory, so we can free it later on. And then say, where do we start running from? Right, RIP. And what's our stack pointer? The RCX is what happens when you return from a system call. It's actually looking in RCX. I don't think that one has an effect. All right, so now switch UVM. This sets the CR3. Clear up the old page directory, and then now we have our new process. So we're returning. So for this one, it's not so complicated, because when you return from exec, you are the new process. Right? So from the point of the kernel, nothing really changed. We just manipulated the process a little bit. We're just returning back out. But of course, we're going back out to something that didn't exist before. We're going back out to the ELF entry in the new program. Questions on that part? Okay, so all of this is necessary in order to maintain this process illusion, right? We're doing all of these things so that the process gets the impression that, oh, I have the machine to myself. I have my own virtual memory. No one else gets to play with my registers, even though we're switching thousands of times a second, right? So there's a little bit of extra bookkeeping required. That's what we're looking at. Okay, so now the exec here, we return, and we're going to go straight to main for echo, right? The first instruction of main in echo, let's see actually what it looks like. Can't be very complicated. All right, so we're jumping to here. Okay, so it's printing out all the string arguments one by one with a string or let's see, an empty space or a new line, depending on how many arguments are left. And then we're done. Okay, so the printf calls write, and we'll skip all those extra system calls, but eventually we get to exit. So that's the last bit. And again, this exit is usually implied, right? In a normal libc, the exit is from the function that called main. So the entry point is not actually main, it's start. And start calls main and then calls exit. But here we explicitly call exit. All right, so this exit is then sysexit. Which is another system call. And you may have noticed that there's there's this exit as well. So sysexit versus exit. This is just a normal function inside of the kernel, right? Nothing special about that. It actually performs the same thing that sysexit does, and we'll find sysexit eventually calls that, right? But there's other reasons why you might want to exit a process that isn't the process asked for it. And specifically, if the process did something bad, then we kill it. Okay, so let's just take a look at sysexit to make sure it doesn't do anything too fancy. Oh, this is proc. It should be in sysproc. Right. That wasn't too fancy. All right, so what does exit do? Well, we have to close our open files because, well, actually, what does this file close do? I think it's going to decrement the reference count so that we free up those entries in the F table? Yeah. Free up the entry in the F table if no one else is using it. This is never going to happen for the files that we have open. Right? Standard in, standard error, standard out. SH is holding on to those, init is holding on to those, so they're actually not going to get closed. But if you had opened another file, you know, open any file you want, then this is when it does get closed. Actually, it's a little curious. It's something you wouldn't necessarily think of. Say you open a file and then you sysexec. Right? Just open any old file and sysexec. That also gets copied, right? So now you're you don't only have 0, 1, and 2. You have file descriptor 3 open, running some arbitrary program. Yeah.
This might be a dumb question, but why does the loop start at file descriptor 0 if standard in is file descriptor 0?
Well, we're not going to be using it anymore, so we ought to be closing it.
Did you just say? Oh. Is this per process?
Yeah,
Oh,
exit.
okay,
Right.
okay.
So this doesn't actually, you know, in the end, it doesn't free up the entry. So we should look at this. Let's dive in here just to make sure. I think usually things get more clear when you see the code, at least to me. Right. So we're decrementing ref, and if there's still more than 0 entries, well, we're not going to do anything more. Otherwise, it's time to actually close this file down. Right? So that probably means different things depending on what kind of file it is. But it ought to at least, if we're an inode and we had done some writing to it, now is the time to write anything that remains out to disk. Sometimes things might be waiting in the cache. We have to make sure everything's out to disk. If it's a pipe, whoever is listening to this pipe on the other end needs to know that there isn't anyone left. So we actually we wake them up. It looks like, let's see, if you close the other end of a pipe, then they will get a 0 read. They were waiting to read from it, and now they got a 0 back, and 0 means that there wasn't anything more. Like they got 0 bytes, and that means the pipe is closed, if I remember correctly. So we actually, so what happens is you wake it up even though there's nothing for them to read. That's really what happens. Okay, so that was file close. What were we doing? We were doing exit, right? This is just to be nice. Doesn't actually have any effect. Yeah. So I was saying about those extra file descriptors. So if you open some files and then exec, then you'll have a binary that's running with some file descriptors it doesn't know about. Like they're sort of like arguments, sort of implicit arguments. So you could, in principle, scan for other open file descriptors to see what the program that started you was up to. I don't know why you would want to do that. With bash, there's also a way to kind of open a file before you start running. I don't remember how you do that. Like, you can pass in something on the command line like this. Let's see, you can say like cat for the file, something like this, and now cat will have file descriptor 4 open with the file. I think it's something like that. Anyway, there's a little bit left over when you exec. I guess that's the point here. Okay, so now that we're closed, let's see, what else are we doing? Oh yeah, current working directory. We had that open, now we close it. Why would we want to open and close a working directory? Well, at least in a normal OS, I don't actually know how it's being used in x86, but at least in a normal OS, if someone deletes the directory that you're running in, it would get awkward. So deleting it is fine, making it so it doesn't show for the user, but your program, when you next try to read something from your local directory, can't just be gone. And so this kind of holds on to the working directory until you're finished running. And I'm not exactly sure what the purpose is of it in x86. All right, so the parent called sh calls this wait, right? This is where we wake up the parent. Let's actually take a look at wake up too. That's how you wake something up. This channel thing is just like an ID. So you say there's just a number. You can wait for this number, or you can wake up that number. So if you're waiting for the number, that means you're setting your P channel to that value. And when you wake up that number, well, you roll through here all the processes, see if there's anyone sleeping, waiting for that channel. Well, then we set their state to runnable. That's all there is to waking up a process. And this is the same pattern that we've seen somewhere else. Actually, I don't know if we've seen this before. Maybe we haven't. No, that may have been last semester. I should explain this. So there's a wake up 1 and there's a wake up. See, here we're applying this p-table lock. And then we just call wake up 1. The assumption is when you call wake up 1, you hold the p-table lock. So why not just acquire the p-table lock in here instead? And not have all this extra complication. You're going to need to use this pattern in future homeworks. So good one to think about. What happens if you try to acquire a lock when you're already holding the lock?
You block.
You'll block forever. Yeah. Or in the XV6 case, because they're a teaching OS, they actually detect this fact and they panic instead. I don't think that that's common, because there's extra cost in keeping track of which process is holding it. But yeah, actually, let's just see how that works. So here, if we are already holding the lock, right? If the lock is locked and the locking CPU is us, well, then we panic. Okay. So sometimes when you want to wake someone up, you're already holding the p-table lock, right? And then you have to call this. If you're not holding the p-table lock, well, then we use the normal wake up. And there's a lot of that. There's a lot of these patterns in the code, because oftentimes you are holding the relevant lock. Right? So in this case, I think we are holding it. We will find out shortly. We call wake up 1, so indeed we are holding it. We're holding it because we are manipulating the the process table at this point, right? This is a shared data structure. You have to hold a lock if you're manipulating a shared data structure. It's right there. We acquired it, and then we change some parents around in the P table, and then at some point inside of SCED we release it. Actually, no. When you start running SCED, you're also required to be holding the P table lock. So it's actually when we get out through switch into the scheduler, at some point it gets released. Okay, so what's going on here? Well, we're killing ourselves. It may well be that there are some children of ours that will now no longer have a parent, and that's not okay. Parents are required because parents clean up from dead children. So we have to give all our children to our parent, and then we're good. Let's see. Well, this is interesting. This seems a little bit iffy, unethical, right? So you have a zombie child, and you tell the grandparent to clean it up. I don't know. You ought to be cleaning up after your own children, I think. But okay. For the other ones, they're still alive. It seems reasonable. If you're dying, let someone else take care of it. Okay. Maybe the rules aren't the same for processes. And so finally, we set our state to zombie. Does anyone remember? Why are we using the zombie process, zombie state? We could just set it to unused and then call SCED.
Someone has to clean up all the resources which the process has.
Someone has to clean up after the process. Well, we're running. Why don't we clean it up?
How can you clean it up if you're still running?
Which resources are we talking about here?
The page table.
The page table, yeah, that needs to get freed. It would get really weird if you free up your own page table and then try to call SCED, because you don't have a pointer anymore that goes anywhere sensible. So that's a very good one. And yeah. So that's a good one. And then there's the kernel stack, same thing. Even if we could somehow magically make the page table go away, the kernel stack, we can't call SCED without having a stack. So we can't free the kernel stack either. Can't call anything without having a stack. Okay, so we just say we need cleanup, and then we call SCED, and after that, it's it. That's it. We're not coming back. Let's see. Questions? So I think we'll have we'll certainly have some questions on this sort of thing in the final. We'll probably have some question on processes and this whole process in the midterm as well. So I think it's a good idea to take a look in the textbook at the virtual memory layout, the process. It's not like chapter 1, chapter 2 like that. It's actually, I think, chapter 8 or something is where we're starting, and then going back. But the virtual memory is very good. So sort of overall OS design somewhere early on, and then the process abstraction. Those would probably be good chapters to review. And then, of course, the code. Okay. Trying to think of what we should do in the last 5 minutes. I don't have any good ideas. We can stop now, or we can discuss anyone have any interesting questions?
Did you get the changes that you made into the repo?
Yep, it's all pushed in. Did I explain what the problem was?
I think you may have posted a note.
Yeah. In fact, I forgot now what it was all about. Oh, yes. That was a beast of a bug. Yeah, so it does make sense to call switch UVM whenever you change the page table, it turns out. Yeah. Except perhaps on a page fault, like we saw last time. Okay, I think we'll just stop a few minutes early then. Or did you have another?
One small question. So basically,
Yeah.
For the vector will be after processes, right?
Yeah, yeah, and we won't have like we won't have anything that we didn't talk about. So there's still stuff left in processes. In particular, I think scheduling, various different ways of scheduling processes, and threads, of course, and a little bit of this and that. But yeah, this is sort of the basics that we covered. Okay, good. So I'll see you next week then.